Imagine for a moment a flash so bright it outshines entire galaxies. A single burst of energy releasing more power than our sun will produce in its entire lifetime. This isn't science fiction. It's happening right now, scattered across the cosmos, in events so violent they warp the fabric of space itself. Welcome to the universe's most energetic explosions, where the rules of physics are pushed to their limits, and the sheer scale of destruction is matched only by the beauty of creation. These cosmic fireworks aren't just spectacles, they're the architects of the universe, forging elements, shaping galaxies, and even influencing the very conditions that made life on Earth possible. Think about that for a second. The gold in your jewelry, the iron in your blood, these were likely born in the heart of a dying star, hurled across space by one of these cataclysmic detonations. From gamma-ray bursts, which are so powerful we can detect them from billions of light years away, to supernova that light up the night sky for weeks, these explosions are the universe's way of reminding us how small we really are, and yet how connected we are to something so much bigger. And here's the wild part, we're only just beginning to understand them. Every new discovery peels back another layer, revealing secrets that challenge everything we thought we knew about energy, time, and the origins of everything around us. So buckle up, because over the next few minutes, we're diving deep into 30 facts about these unimaginable cosmic events, facts that will bend your mind, shake your perspective, and maybe even make you see the night sky a little differently. We'll explore how a single explosion can release more energy in 10 seconds than our sun will in 10 billion years, how some of these bursts might hold the key to unlocking the mysteries of dark matter, and how, without them, the universe as we know it wouldn't exist. This isn't just a journey through space, it's a journey through time, through chaos, and through the very forces that sculpted reality itself. Ready? Let's go. Gamma-ray bursts, or GRB, are the universe's most violent explosions, capable of unleashing more energy in mere seconds than our sun will emit over its entire 10 billion-year lifespan. First detected in the late 1960s by military satellites designed to monitor nuclear tests, these bursts puzzled scientists for decades. At first, they seemed like random flashes of high-energy radiation coming from deep space. But as technology advanced, researchers realized these weren't just cosmic hiccups, they were the death cries of massive stars or the catastrophic collisions of ultra-dense neutron stars. What makes GRBs so mind-boggling is their sheer power. A single burst can outshine entire galaxies, emitting as much energy as a supernova, but concentrated into a narrow beam of gamma rays traveling at nearly the speed of light. Their durations vary wildly, from milliseconds to several minutes, revealing clues about their origins. Short bursts lasting less than 2 seconds are thought to come from neutron stars smashing together, rippling spacetime with gravitational waves in the process. Long bursts, on the other hand, are tied to the collapse of massive stars, where the core implodes into a black hole while the outer layers explode in a supernova visible across the cosmos. These explosions don't just light up the night, they shape it. The heavy elements forged in their aftermath, like gold and platinum, are scattered into space, eventually finding their way into planets and even life itself. And because their light travels billions of years before reaching us, GRBs act as cosmic time capsules, offering glimpses into the universe's most turbulent eras. Some scientists even speculate they might have played a role in Earth's past, with ancient bursts potentially altering our planet's atmosphere or triggering mass extinctions. The more we learn, the clearer it becomes. Gamma-ray bursts aren't just spectacular fireworks, they're the universe's way of rewriting its own history. To grasp the raw, mind-bending power of gamma-ray bursts, let's put it this way. If the sun were a candle, a typical GRB would be a thermonuclear fireball the size of a city, burning brighter than a billion suns for a few terrifying seconds. These cosmic explosions release more energy in that fleeting moment than our Sun will generate over its entire 10 billion-year lifespan. That's not just impressive, it's almost incomprehensible. Picture every nuclear weapon ever built detonating simultaneously, then multiply that by 1,000,000. That's roughly the energy packed into a single gamma-ray burst. If one occurred within a few thousand light-years of Earth, the radiation alone could strip away our ozone layer, triggering a catastrophe. Fortunately, most GRBs happen in distant galaxies, but their sheer scale forces us to rethink how energy operates in the universe. What's even wilder, this energy isn't radiated in all directions like a supernova. Instead, it's focused into narrow, high-speed jets like cosmic laser beams slicing through space. If you were unfortunate enough to be directly in their path, the burst would appear blindingly bright even from billions of light-years away. From any other angle, you might miss it entirely. That's why we detect only a fraction of them, even as they happen almost daily across the cosmos. Scientists measure this energy in ergs, a unit so small that everyday objects require trillions of them. A GRB, though, can unleash up to 10 to the 54 ergs. To put that into perspective, that's more energy than our entire Milky Way galaxy emits over several years, compressed into a single, catastrophic event lasting mere seconds. It's like detonating all the stars in 100 galaxies at once, and here's the kicker. This energy isn't just wasted. It seeds the universe with heavy elements, fuels the birth of new stars, and even influences the structure of galaxies. Without these violent outbursts, the cosmos as we know it might not exist. So the next time you look up at the night sky, remember, somewhere out there, a gamma-ray burst is rewriting the rules of reality, one cataclysmic explosion at a time. When a star more than 20 times the mass of our Sun reaches the end of its life, it doesn't just fade away, it goes out with a bang so colossal it defies imagination. This is the hypernova, a rare and extreme version of a supernova, and it's the engine behind the universe's most powerful long gamma-ray bursts. Unlike ordinary supernova, which leave behind neutron stars or black holes, hypernova are so violent they can tear apart the very fabric of space-time, releasing energy on a scale that borders on the absurd. The process begins deep inside the star's core, where nuclear fusion has been forging heavier and heavier elements over millions of years. When the core finally exhausts its fuel, gravity wins catastrophically. In a fraction of a second, the core collapses inward, compressing matter so tightly that protons and electrons merge into neutrons, releasing a flood of neutrinos in an unimaginable burst of energy. But in hypernova, something even more extraordinary happens. The collapse doesn't stop at a neutron star, it keeps going, forming a black hole with a spinning disk of superheated material around it. This is where the real fireworks begin. Twin jets of plasma, accelerated to nearly the speed of light by the black hole's insane magnetic fields, punch straight through the star's outer layers. When these jets break free, they unleash a torrent of gamma rays, a gamma-ray burst so intense it can be detected halfway across the observable universe. Meanwhile, the rest of the star explodes outward in a supernova, ejecting material at thousands of kilometers per second. What's left behind depends on the star's original mass. Sometimes it's a black hole, a gravitational monster so dense even light can't escape. Other times, if conditions are just right, the core might form a magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth. These cosmic powerhouses spin rapidly, emitting beams of X-rays and gamma rays that sweep across space like celestial lighthouses. But here's what's really mind-blowing. Without these violent deaths, life as we know it wouldn't exist. The explosions scatter heavy elements like iron, gold, and uranium into space, seeding future generations of stars and planets. Every time you see a long gamma-ray burst, you're witnessing the birth of the building blocks of life, forged in fire, scattered by destruction, and destined to become part of something new. While long gamma-ray bursts come from the deaths of massive stars, their shorter counterparts lasting less than 2 seconds have an equally spectacular origin: the violent merger of two neutron stars. These ultra-dense stellar corpses, each packing more mass than our Sun into a city-sized sphere, collide with such force that they ripple space-time itself, sending out gravitational waves while unleashing a blinding flash of gamma rays. The first confirmed detection of this cosmic dance came in 2017, when gravitational wave observatories picked up a signal labeled GW170817. Just 2 seconds later, telescopes around the world spotted a matching short gamma-ray burst emanating from the same patch of sky. This historic event didn't just confirm decades of theory, it opened a new era of multi-messenger astronomy where scientists could study the same cataclysm through gravity, light, and even subatomic particles. What makes these collisions so explosive? Picture two neutron stars locked in a deadly orbital embrace. As they spiral closer, tidal forces distort their shapes, flinging streams of superheated material into space. When they finally collide, the impact generates temperatures exceeding 1 trillion degrees hot enough to forge heavy elements like gold, platinum, and uranium in a process called rapid neutron capture. The resulting fireball shoots out relativistic jets, producing the gamma-ray burst, while the merged core collapses into either a heavier neutron star or a black hole in milliseconds. But the real surprise from GW170817 was the kilonova, an afterglow 1,000 times brighter than a typical nova, powered by radioactive decay of freshly minted heavy elements. Observations revealed that a single merger can eject up to several Earth masses of gold and platinum into space. That means the ring on your finger or the circuitry in your phone likely contains atoms forged in one of these unimaginable cosmic smash-ups. Beyond enriching the universe, these events serve as cosmic laboratories. The gravitational waves they produce let scientists test Einstein's theories under extreme gravity, while the gamma-ray bursts act as beacons illuminating the distant cosmos. Every neutron star collision we detect adds another piece to the puzzle, revealing how the most exotic objects in the universe shape everything from the emptiness of space to the very atoms in our bodies. The blinding flash of a gamma-ray burst isn't the end of the story, it's just the opening act. Within seconds of the initial explosion, something extraordinary happens. The burst leaves behind a lingering afterglow that can shine across the electromagnetic spectrum for days, sometimes even weeks. This fading light show, visible in X-rays, radio waves, and visible light, transforms a fleeting cosmic event into a scientific goldmine. Unlike the gamma rays themselves, which vanish almost instantly, the afterglow is created when the jet of material slams into surrounding gas and dust at nearly the speed of light. The collision generates shock waves that heat the interstellar medium, causing it to glow like a fading ember. This glow is far less energetic than the initial burst, but just as valuable because it allows astronomers to finally pinpoint where these explosions are coming from. Without this afterglow, GRBs would remain cosmic mysteries, vanishing before telescopes could even turn toward them. Here's how it works. As soon as satellites detect a burst, observatories worldwide receive alerts, swiveling their instruments toward its rough direction. The afterglow acts like a cosmic breadcrumb trail, guiding astronomers to the exact galaxy, or sometimes even the exact star system where the explosion occurred. By analyzing its brightness across different wavelengths, scientists can calculate the burst's distance, energy, and even the environment around it. Some afterglows reveal dense clouds of gas, suggesting the star exploded inside a stellar nursery. Others show cleaner surroundings, hinting the progenitor star had already cleared its neighborhood with fierce stellar winds. But the real magic happens when the afterglow fades. As it dims, it often uncovers something even more fascinating, the faint light of a supernova or kilonova lurking beneath. This is the smoking gun that confirms whether the burst came from a collapsing star or colliding neutron stars. In one remarkable case, astronomers watched a supernova brighten days after the gamma rays faded, proving the two events were linked. Perhaps the most astonishing thing about these afterglows is how far we can see them. Some originate from galaxies so distant their light has traveled for over 13 billion years, meaning we're witnessing explosions that occurred when the universe was just a fraction of its current age. Each one is a time capsule, offering clues about how stars lived and died in the cosmos's earliest chapters. So while gamma-ray bursts might steal the spotlight with their raw power, it's their quiet, lingering afterglows that truly unlock the universe's secrets. Without them, we'd still be staring into the dark, wondering where these titanic explosions came from, and what they're trying to tell us about the life and death of stars. 13 billion years ago, when the universe was a mere infant just 630 million years old, a star died in one of the most violent explosions imaginable, and its light finally reached us in 2009. Designated GRB 090423, this gamma-ray burst holds the record as the most distant ever detected, offering us a direct glimpse into the cosmos's chaotic adolescence. What makes this burst so extraordinary isn't just its mind-bending distance, it's what its existence tells us about the early universe. At that time, the cosmos was barely 5% of its current age, still emerging from the cosmic dark ages when the first stars and galaxies were just beginning to ignite. The fact that such a powerful explosion occurred so soon after the Big Bang suggests massive stars formed and died at a staggering pace, seeding the universe with heavy elements far earlier than we once thought possible. When telescopes like NASA's Swift satellite caught the initial flash, astronomers knew immediately they were seeing something special. The afterglow's redshift, a measure of how much the universe has stretched the light during its journey, was a record-breaking 8.2. To put that in perspective, the light from GRB 090423 had traveled for nearly the entire history of the cosmos before reaching us, stretching from ultraviolet to infrared along the way. By the time it arrived, the universe had expanded so much that the burst's home galaxy, if it still exists, is now over 30 billion light-years away. Studying this ancient explosion revealed surprises. The burst's energy profile matched those of later GRBs, proving that even in the universe's youth, stars could collapse with the same catastrophic force we see today. But there's a twist. The afterglow lacked signatures of iron and other heavy elements typically seen in modern supernova. This suggests the first stars might have been chemically pristine, born from only hydrogen and helium, their deaths scattering the first metals into the primordial cosmos. Beyond rewriting stellar history, GRB 090423 acts as a cosmic flashlight. Its beam pierced through clouds of neutral gas that filled the early universe, allowing astronomers to study conditions during an era too distant for most telescopes. The burst's light even hinted at the timeline of cosmic reionization, the epoch when the first starlight burned away the fog of hydrogen that once shrouded the cosmos. Every photon from this explosion is a relic carrying clues about how the universe grew up. Without such distant bursts, we'd have no way to probe these ancient epochs directly. GRB 090423 isn't just a record holder, it's a time machine, showing us the moment the universe began building the ingredients for everything we know. Picture a gamma-ray burst occurring within just a few thousand light-years of Earth, close enough that its fury wouldn't just be a distant spectacle but a direct threat. The sheer energy of such an event would flood our solar system with high-energy radiation, capable of shredding the ozone layer that protects life from the sun's lethal ultraviolet rays. Within moments, the sky might glow with an eerie, unnatural light, followed by a cascade of atmospheric changes that could trigger mass extinctions. This isn't just hypothetical. Some scientists believe Earth may have already endured such an event hundreds of millions of years ago, leaving behind traces in the fossil record. But here's the good news. The odds of a nearby GRB hitting Earth are astronomically low, literally. For a burst to pose a danger, two things must align perfectly. It has to happen relatively close by, and its deadly jets must be pointed directly at us. Given how narrow those beams are, the chance of one lining up with our planet is vanishingly small. Even in our own Milky Way, where GRBs are rare to begin with, most massive stars that could produce them are nowhere near our cosmic neighborhood. The closest potential candidate, a star named Eta Carinae, sits safely 7,500 light-years away, far enough that its eventual explosion, while spectacular, won't threaten life on Earth. What's more, the universe seems to have built-in safeguards. Dense regions where GRBs are common, like bustling stellar nurseries, are typically found far from the quieter galactic suburbs where solar systems like ours reside. Even if a burst occurred within striking distance, Earth's atmosphere and magnetic field would absorb some of the initial blow, though the long-term effects could still be devastating. While it's fun to imagine doomsday scenarios, the reality is far less dramatic. GRBs serve as a humbling reminder of the universe's raw power, but they're also incredibly rare on human timescales. In fact, you're far more likely to win the lottery repeatedly than to witness a lethal gamma-ray burst in your lifetime. So instead of worrying, consider this. Every GRB we detect is a reminder of how fragile and precious our planet is, tucked safely into a quiet corner of a galaxy that's kind enough to keep its fireworks at a distance. At first glance, a supernova might seem like the ultimate cosmic explosion, an event so bright it outshines entire galaxies. But in the universe's hierarchy of violence, there's something even more extreme, the hypernova. While both mark the deaths of massive stars, the difference between them is like comparing a campfire to a volcanic eruption. An ordinary supernova occurs when a star at least 8 times more massive than our Sun exhausts its nuclear fuel. The core collapses in seconds, triggering a shock wave that blasts the star's outer layers into space at incredible speeds. For weeks or months, the expanding debris glows brightly enough to outshine billions of stars. These explosions are rare in our galaxy, happening perhaps twice a century, but they're vital for spreading heavy elements like oxygen, silicon, and iron across the cosmos. Hypernova take this destruction to another level entirely. These events involve stars with masses exceeding 20 suns, where the core collapse doesn't just form a neutron star. It creates a black hole with such ferocious energy that it launches relativistic jets piercing through the dying star. The result, a gamma-ray burst accompanied by a supernova hundreds of times more energetic than normal. While conventional supernova release around 10 to the 44 joules of energy, hypernova can surpass 10 to the 46, enough to power human civilization for trillions of years. One of the most famous examples, SN 1998 BW, changed astronomy forever. Discovered alongside a gamma-ray burst, it provided the first concrete evidence linking hypernova to long GRBs. Unlike typical supernova, this explosion showed asymmetric, jet-driven features and velocities exceeding 30,000 kilometers per second, 3 times faster than normal. Its light curve also stayed bright far longer, suggesting extra energy from the central black hole's activity. What makes hypernova truly exceptional isn't just their power, but their rarity. For every 100 supernova, only 1 or 2 reach hypernova status. They require perfect conditions, a rapidly spinning massive star with relatively low metallicity to minimize energy loss through winds. This rarity means we've observed only a handful definitively, each one offering new puzzles. Some show bizarre chemical signatures, while others leave behind magnetars instead of black holes. The legacy of these explosions stretches beyond their immediate violence. Hypernova are likely responsible for producing much of the universe's heaviest elements, from gold to uranium, through rapid neutron capture in their extreme environments. They might even influence galaxy evolution, with their energetic jets regulating star formation in their vicinity. So while a supernova marks the end of a star's life, a hypernova reshapes the cosmos around it, proving that even in death, the most massive stars never go quietly. There exists a class of stellar explosions so devastating that not even a black hole remains, only an empty void where a star once blazed. These are pair instability supernova, the universe's most self-destructive fireworks, where a star doesn't just collapse or explode but annihilates itself down to the last atom. Unlike hypernova or typical supernova, which leave behind neutron stars or black holes, these events obliterate everything, including their own cores, in a runaway thermonuclear chain reaction that defies conventional physics. The trigger lies in a bizarre quantum quirk. When a star between 100 and 300 solar masses reaches the end of its life, temperatures in its core soar above 1 billion degrees, so extreme that photons begin spontaneously transforming into particle-antiparticle pairs. This process saps the core's radiation pressure, the very force that's been holding the star up against gravity. Without that support, the core suddenly contracts, heating up further and igniting oxygen fusion in a catastrophic feedback loop. The entire star becomes a thermonuclear bomb, with fusion waves rippling outward until they reach the surface. The resulting explosion doesn't just blow off the outer layers, it vaporizes the star completely, leaving no remnant behind. What makes these explosions especially fascinating is their role in the early universe. The first generation of stars, called population 3 stars, likely included many in this mass range. When they died as pair instability supernova, they flooded the primordial cosmos with staggering amounts of heavy elements like silicon, magnesium, and iron, far more than ordinary supernova produce. This chemical enrichment may have jump-started the formation of later generations of stars and planets, seeding the universe with ingredients it couldn't have forged otherwise. Yet for all their power, we've never definitively observed one. The stars capable of producing them are vanishingly rare today, as modern galaxies lack the pristine hydrogen-helium gas needed to form such behemoths. But astronomers are hunting for chemical fingerprints in ancient, ultra-metal, poor stars' time capsules that might preserve debris from these early explosions. One tantalizing candidate, a star in the Milky Way's halo labeled J0313-6780, shows bizarrely low amounts of heavy elements like iron but unexpected abundances of lighter ones, matching predictions for pair instability supernova debris. The hunt continues because understanding these explosions isn't just about stellar death, it's about cosmic rebirth. Without them, the universe might have remained a chemical wasteland, devoid of the diversity needed to build planets, oceans, or life. Every time astronomers spot an unusually bright supernova in a distant galaxy, they ask, could this be the one? A relic from an era when stars didn't just die, but erased themselves from existence to light the way for everything that followed. In the vast tapestry of cosmic violence, few objects match the sheer ferocity of a magnetar, a neutron star so magnetically charged it bends reality itself. Imagine a stellar corpse the size of Manhattan, spinning faster than a kitchen blender, with a magnetic field a quadrillion times stronger than Earth. These aren't just dense relics of dead stars, they're cosmic powder kegs capable of erupting without warning in flares that outshine our sun by a factor of quintillions. Take December 27, 2004, a date astronomers won't soon forget. Without any warning, a magnetar 50,000 light-years away in the constellation Sagittarius unleashed a blast of energy so intense it briefly outshone the full moon. In just 0.2 of a second, it released more power than our sun has emitted in the last 250,000 years combined. The flare, dubbed SGR 180620, was so bright it temporarily blinded space telescopes and bounced off the moon, creating secondary X-rays detectable from Earth. But the real shock came when scientists realized this distant explosion had physically affected our planet, ionizing Earth's upper atmosphere to a depth normally seen only during severe solar storms. What makes magnetar flares so uniquely terrifying is how they warp the very fabric of space around them. Their magnetic fields are so strong they can twist the star's solid crust, creating starquakes that crack open the surface like an eggshell. When these fractures occur, they release pent-up magnetic energy in bursts of gamma rays and X-rays, a process called a starquake flare. The energy doesn't radiate evenly in all directions but follows twisted magnetic field lines, creating beams of radiation that sweep across the cosmos like cosmic searchlights. Surprisingly, these apocalyptic events might be more common than we thought. Before 2004, astronomers assumed magnetar flares were rare, perhaps occurring once per galaxy per century. But improved monitoring has revealed smaller eruptions happening several times per year across the Milky Way. Some magnetars even produce mini flares, which, while less catastrophic, still pack enough punch to disrupt satellite communications and fry unshielded electronics across entire star systems. Yet for all their destructive potential, magnetars serve a crucial cosmic purpose. Their violent flares inject heavy elements into interstellar space and may help explain mysterious phenomena like fast radio bursts. They also act as natural laboratories for physics we can't replicate on Earth, where magnetic fields are strong enough to distort the quantum vacuum itself. Every time one erupts, it's a reminder that the universe still holds forces beyond our wildest imagination, forces that don't just shape distant galaxies, but occasionally reach across space to tap us on the shoulder and say, "Pay attention." At the heart of some of the most luminous objects in the universe lies a paradox, a black hole so voracious it becomes brighter than 1,000,000,000,000 suns. These are quasars, the blazing cores of distant galaxies where supermassive black holes, weighing billions of times our sun's mass, devour entire stars while belching out jets of plasma that stretch across millions of light years. What makes them truly astonishing isn't just their appetite, but how they transform cosmic destruction into radiant energy, outshining every star in their host galaxies combined. The secret lies in the physics of chaos. As gas, dust, and even whole stars spiral toward the black hole's event horizon, friction heats this material to millions of degrees, creating a swirling disk of superheated plasma called an accretion disk. The inner regions of this disk glow so intensely they emit more light than all the stars in the Milky Way, turning the quasar into a beacon visible across the observable universe. But the real spectacle happens above and below the disk, where twisted magnetic fields channel some of this infalling material into narrow, high-speed jets shooting outward at nearly the speed of light. These jets are nature's ultimate particle accelerators. Charged particles whipped to relativistic energies within them produce gamma rays, X-rays, and radio waves detectable billions of light years away. One of the most powerful known quasars, 3C273, boasts jets stretching over 200,000 light years, twice the diameter of our galaxy, carrying enough energy to reshape entire galactic neighborhoods. If placed in our cosmic backyard, such a jet would sterilize every planet in its path, its radiation overwhelming atmospheres and frying DNA with ruthless efficiency. Yet quasars aren't just destroyers, they're cosmic architects. Their outflows regulate star formation in their host galaxies, heating surrounding gas so efficiently they can suppress new star birth for eons. Some astronomers believe this feedback mechanism explains why massive galaxies today aren't even larger. The quasars at their cores essentially starved themselves by shutting down their own fuel supply. The most mind-bending part, every quasar we see is a glimpse into the universe's violent youth. Because their light takes billions of years to reach us, we're witnessing an era when galaxies were still taking shape, their central black holes feasting on the abundant gas of the early cosmos. Today, most quasars have gone quiet, their fuel exhausted, but their legacy lives on in the supermassive black holes lurking at the centers of galaxies, ours included. So when you look up at the night sky, remember, the Milky Way's own dormant giant, Sagittarius A, was once a quasar too. its glory days lost to time, but its presence a silent reminder of the universe's fiery adolescence. Somewhere in the cosmos, right now, a star is being stretched like cosmic taffy, pulled apart strand by strand in the crushing grip of a black hole's gravity. This isn't just destruction, it's a spectacle known as a tidal disruption event, where a star ventures too close and becomes the universe's most unwilling fireworks display. The process begins when the black hole's tidal forces, the difference in gravity between the star's near and far sides, overwhelm the star's own gravity. What happens next is both brutal and beautiful. The star is shredded into a stream of plasma, some of which spirals into the black hole at nearly light speed, while the rest is flung outward in a dazzling flare that can outshine entire galaxies for months. Take Assassin 15LH, a record-breaking tidal disruption event discovered in 2015. At its peak, this cosmic cataclysm blazed with the luminosity of over 570 trillion suns, 20 times brighter than the entire Milky Way. What made it especially bizarre was its location, not in a bustling galactic core where supermassive black holes typically lurk, but in a quiet, unassuming galaxy with no signs of prior activity. Scientists initially debated whether it was even a tidal disruption event or some new kind of hypernova, until detailed observations revealed the telltale signatures of a star being torn apart. The physics behind these events is just as fascinating as the light shows they produce. As the star's material falls toward the black hole, friction heats it to millions of degrees, creating an accretion disk that emits X-rays and ultraviolet light. But here's the twist: some of the debris doesn't fall in immediately. Instead, it collides with itself in chaotic orbits, producing shock waves that glow fiercely in visible light, a signature that helps astronomers distinguish tidal disruptions from other cosmic explosions. What's truly remarkable is how much these events reveal about black holes themselves. By studying the flare's brightness and duration, scientists can estimate the black hole's mass and spin. In rare cases like Assassin 14AE, they've even caught the disruption in its earliest phases, watching as the star's outer layers were stripped away before the final cataclysmic rupture. But tidal disruptions aren't just about annihilation, they're also about creation. The extreme conditions in the accretion disk forge heavy elements, while the ejected material enriches interstellar space with stellar debris. Some theorists even speculate that these events could trigger star formation in their host galaxies, turning destruction into new beginnings. So the next time you look up at the night sky, remember, somewhere out there, a star is meeting its dramatic end, not with a whimper, but with a blaze of glory that lights up the cosmos. A collision between two supermassive black holes is the universe's ultimate heavyweight fight, a cataclysmic showdown where the energy released dwarfs every supernova, hypernova, and gamma-ray burst combined. Picture two gravitational titans, each weighing millions or even billions of suns, locked in a death spiral that shakes the fabric of space-time itself. When they finally merge, the explosion doesn't produce light or gamma rays, but something far more profound: gravitational waves that ripple across the cosmos at the speed of light, carrying with them a snapshot of the most violent event since the Big Bang. The numbers involved are almost nonsensical. During the final moments of such a merger, the energy radiated in gravitational waves can briefly outshine the light from every star in the observable universe combined. In one theoretical scenario, two black holes, each with 10 billion solar masses, could release a staggering 10 to the 61 ergs of energy, more than the total output of 100 trillion supernova. That's enough to power human civilization for a timescale longer than the current age of the universe, but detecting these cosmic tremors isn't easy. Unlike stellar mass black hole mergers, which produce high-frequency waves detectable by observatories like LIGO, supermassive collisions hum at frequencies too low for current instruments. That's where pulsar timing arrays come in, networks of ultra-precise cosmic clocks called millisecond pulsars. By monitoring tiny shifts in their rhythmic radio pulses over decades, scientists can catch the faint gravitational wave background from countless supermassive mergers across the cosmos. The first hints of this discovery came in 2023, when multiple international collaborations reported a low-frequency hum permeating space-time, a chorus of echoes from ancient black hole collisions spanning billions of years. These waves carry secrets about how galaxies evolve, since nearly every large galaxy harbors a supermassive black hole at its core. When galaxies collide, their central black holes eventually spiral together, reshaping their host galaxies in the process through recoil kicks that can fling the merged black hole and entire star clusters into intergalactic space. What's truly mind-bending is the timescale. A single supermassive black hole merger can take millions of years from initial approach to final coalescence, with gravitational waves slowly sapping their orbital energy until the last violent seconds. During that climax, the event horizons stretch and distort like taffy before merging into a single, wobbling black hole that rings down like a struck bell, sending out gravitational waves at characteristic frequencies that reveal its mass and spin. These collisions aren't just cosmic curiosities, they're the engines of galactic evolution. The recoil from a merger can clear entire regions of gas, shutting down star formation or flinging stars into chaotic orbits. Some theorists even speculate that the energy released might trigger new star birth in distant gas clouds. Every ripple in space-time from these titanic mergers carries a message that even the darkest objects in the universe are anything but silent, and their collisions rewrite the rules of physics on scales we're only beginning to comprehend. In the mid-19th century, astronomers witnessed something unprecedented, a star in the southern constellation of Carina suddenly flaring brighter than Sirius, the night sky's usual champion. Eta Carinae, a colossal star already known for its instability, had erupted in an outburst so violent it briefly outshone every star in the Milky Way except one. For years, the spectacle dominated the southern sky, visible even in broad daylight as the star ejected enough material to form 10 suns. Today, we see the aftermath, the iconic homunculus nebula, a bipolar cloud of gas and dust glowing from within, lit by the still furious star at its heart. What made this eruption so extreme? Eta Carinae is no ordinary star. It's a binary system where the primary star weighs at least 90 solar masses, with a luminosity 5 million times that of our Sun. Such behemoths live fast and die young, constantly teetering on the edge of self-destruction. In the 1843 outburst, radiation pressure from the star's core overcame gravity, blowing off its outer layers in a cataclysmic stellar tantrum. But unlike a supernova, the star survived, barely leaving behind a scarred, hyperactive remnant that still hiccups with smaller eruptions every few decades. The real question isn't what happened, it's what's next. Eta Carinae is a ticking time bomb, expected to end its life not with a whimper but with a hypernova. When its core finally collapses, the resulting explosion could produce a gamma-ray burst directed straight at Earth if we're unlucky enough to be in its crosshairs. Even at its safe distance of 7,500 light-years, such an event would bathe our planet in enough high-energy radiation to trigger atmospheric changes. Some researchers speculate past eruptions like this might explain oddities in Earth's geological record, like sudden spikes in radioactive isotopes. Yet Eta Carinae's greatest legacy might be the secrets it's already revealed. Its eruptions have shown us how massive stars shed weight before death, like heavyweight boxers cutting water weight before a fight. The homunculus nebula, meanwhile, acts as a cosmic lab for studying stellar winds, shock fronts, and even the formation of cosmic dust material that could one day coalesce into new planets. Every time this star coughs, it sends astronomers scrambling, offering fresh clues about the lives and deaths of the universe's most massive stars. And when it finally explodes, it won't just be a spectacle, it'll be a masterclass in how the universe recycles destruction into creation. In the year 1054, Chinese astronomers looked up at the sky and saw something impossible, a new star blazing brighter than Venus, visible even in broad daylight for 23 days. They called it a guest star, unaware they were witnessing one of history's most famous supernovas, the violent death of a massive star whose remnants we now know as the Crab Nebula. Nearly 1,000 years later, this cosmic explosion still captivates scientists, not just as a relic of the past, but as a powerhouse shaping our understanding of the universe's most extreme physics. What makes the Crab Nebula so special isn't just its historical significance, it's the frenetic activity still unfolding within its swirling tendrils of gas. At its heart lies a pulsar, a neutron star spinning 30 times per second, whipping charged particles to nearly the speed of light. This cosmic dynamo acts like a natural particle accelerator, far more powerful than anything humans could build on Earth. The pulsar's intense magnetic field channels electrons along its poles, creating twin beams of radiation that sweep across space like a lighthouse, while shock waves from the original explosion continue to heat the surrounding nebula, making it glow across the entire electromagnetic spectrum. But here's where it gets even wilder. The Crab Nebula isn't just a pretty light show. It's a cosmic laboratory for studying high-energy phenomena we can't replicate elsewhere. The nebula's tangled magnetic fields and turbulent plasma create conditions perfect for particle acceleration, producing gamma rays with energies exceeding 100 trillion electron volts, millions of times more powerful than medical X-rays. These particles are so energetic that when they collide with photons, they can spontaneously create matter and antimatter pairs, a process predicted by Einstein's famous equation but rarely observed in nature at this scale. The Crab's influence stretches far beyond its own boundaries. Its steady output of radiation serves as a standard candle for astronomers calibrating instruments, while its pulsar's precise flashes help test Einstein's theory of general relativity. Even its debris field holds clues, traces of heavy elements forged in the original explosion, now scattered across interstellar space. And let's not forget the cultural impact. The supernova's appearance was recorded not just in China, but by indigenous peoples in North America, leaving behind petroglyphs and oral histories that remind us how deeply humanity has always been connected to the cosmos. Perhaps the most astonishing thing about the Crab Nebula is how alive it still feels. Unlike most supernova remnants which fade into obscurity over centuries, this one refuses to go quietly. Its pulsar pumps energy into the nebula so efficiently that the entire structure shines with the luminosity of 75,000 suns, a testament to the raw power of stellar death. Every time astronomers point their telescopes at it, they discover something new, whether it's unexpected gamma-ray flares, intricate gas filaments moving at half the speed of light, or hints of even more exotic physics lurking beneath the surface. The Crab isn't just a relic, it's a reminder that in the universe, destruction and creation are two sides of the same coin, and sometimes the most violent events leave behind the most enduring legacies. Deep in the aftermath of colliding neutron stars, the universe performs its most spectacular alchemy, transforming the debris of dead stars into gold, platinum, and other precious elements that would later become the stuff of planets, jewelry, and even life itself. This dazzling process, called a kilonova, isn't just another cosmic explosion. It's a glowing, multi-colored forge where the heaviest elements in the periodic table are born. And the light show it produces is unlike anything else in the cosmos. When two neutron stars spiral together and merge, the violence of their collision does something extraordinary. The intense pressure and temperature exceeding 1 trillion degrees create a superheated soup of neutrons so dense that atomic nuclei can't stay intact. Instead, free neutrons bombard lighter elements in a frenzy known as rapid neutron capture, or the R process. In just seconds, this process builds up elements like gold, platinum, uranium, and iodine, materials that regular supernova can't produce in significant quantities. But the real magic happens when these freshly minted elements are ejected into space. Unlike a supernova's symmetrical blast, a kilonova sprays debris in all directions at speeds approaching light, creating an expanding cloud of radioactive material. As this cloud cools, the heavy elements within it begin to decay, emitting light across the entire spectrum, from infrared to visible to ultraviolet. The result: a literal rainbow of light that starts out glowing blue from the hottest, fastest-moving material, then gradually shifts to red as the cloud expands and cools over days. The first time astronomers caught this colorful transformation in action was in 2017, during the historic neutron star merger GW170817. Observations revealed something astonishing. The event had produced an estimated 10 Earth masses of gold alone, along with other rare metals. Suddenly, the origins of these elements, long debated among scientists, became clear. Every gold ring, platinum necklace, or uranium fuel rod on Earth likely contains atoms forged in similar cataclysms that occurred billions of years ago. Beyond the bling, kilonovae solve a cosmic mystery. Before their discovery, astronomers struggled to explain how the universe could have so much heavy material when ordinary supernova fell short. Now we know these neutron star collisions are the universe's primary foundries, scattering precious metals across galaxies where they're eventually incorporated into new stars, planets, and even living organisms. The iron in your blood might come from a supernova, but the iodine in your thyroid and the gold in your smartphone, those were likely forged in the heart of a kilonova's fury. So the next time you admire a piece of jewelry or rely on a radioactive isotope in medicine, remember, you're holding a piece of cosmic history, crafted in one of the most violent and beautiful events the universe has to offer. Without these stellar collisions, the periodic table would be missing some of its most fascinating elements, and Earth, along with everything on it, would be a very different place. In the vast silence of space, there are cosmic whispers so fleeting most telescopes would miss them, bursts of radio waves lasting mere milliseconds, but packing more energy than the sun emits in days. These are fast radio bursts, or FRB, some of the universe's most enigmatic signals. First discovered in 2007, these blips appear randomly across the sky, vanishing almost as quickly as they arrive, leaving astronomers scrambling to decode their origins. What makes FRBs so baffling isn't just their brevity, it's their sheer intensity. A typical burst releases as much energy in 1,000th of a second as our sun does over 80 years. Some explode once and disappear forever, while others, like FRB 1210-2, repeat unpredictably, flickering on and off like a cosmic strobe light. These repeating bursts are particularly tantalizing, offering scientists rare chances to pinpoint their locations. One such repeater was traced to a distant, unassuming dwarf galaxy 3 billion light-years away, embedded in a region of furious star formation. The leading suspect, magnetars, those same ultramagnetic neutron stars capable of starquakes and apocalyptic flares. One particularly persuasive case emerged in 2020 when a magnetar in our own galaxy, SGR 1935+215, emitted a radio burst eerily similar to an FRB, albeit weaker. This smoking gun suggested that at least some FRBs could be magnetars throwing magnetic tantrums, their crusts cracking under unimaginable strain as they unleash bursts of radiation across the cosmos. But here's where it gets wild. Not all FRBs fit this neat explanation. Some bursts show bizarre patterns or frequencies that defy current models, sparking alternative theories. Could they be the aftermath of neutron star collisions, producing shock waves in surrounding debris? Or perhaps emissions from cosmic strings, hypothetical defects in space-time left over from the Big Bang? And yes, while scientists generally dismiss it, the idea of extraterrestrial origins occasionally surfaces as playful speculation. After all, a sufficiently advanced civilization might use focused radio bursts as propulsion beams for light sails. though most researchers agree natural explanations are far more likely. The real breakthrough came when astronomers noticed something peculiar about FRBs. Their signals arrive stretched as if they've traversed vast oceans of invisible matter. This distortion, called dispersion, reveals the presence of ionized gas between galaxies, a cosmic web long theorized but difficult to map. By studying how FRBs interact with this intergalactic medium, scientists are essentially using these bursts as flashlights, illuminating the universe's hidden scaffolding. Every new detection peels back another layer of mystery. Some FRBs come with side dishes of X-rays or gamma rays, while others emit polarized light, hinting at extreme magnetic environments. There's even evidence that certain bursts might be lensed, magnified by the gravity of intervening galaxies, offering accidental close-ups of these distant phenomena. Whether they're magnetar screams colliding neutron stars or something even stranger, FRBs remind us how much of the universe remains uncharted. Each time one crackles across the cosmos, it carries a message. That space is far from silent, and even its briefest signals can hold the keys to understanding everything from the birth of stars to the fabric of spacetime itself. On the evening of August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a signal so strong and unusual that the astronomer who discovered it scribbled, "Wow," in the margin of the printout, giving birth to the most infamous mystery in cosmic radio astronomy. Lasting 72 seconds and blaring 30 times louder than the background noise of space, this narrowband radio burst came from the direction of the constellation Sagittarius, matching almost perfectly the predicted signature of an artificial extraterrestrial transmission. What made the WOW signal so electrifying was its frequency, 1420 MHz, a protected band where earthly transmissions are forbidden to avoid interference with radio astronomy. This exact frequency also happens to be where hydrogen, the most common element in the universe, naturally emits radio waves, making it a logical cosmic hello channel any advanced civilization might use. The signal's intensity rose and fell like a passing ambulance siren, exactly as expected if it originated from a fixed point in space and Earth rotation carried the telescope's beam across it. Yet despite decades of follow-up searches, including targeted scans by the Very Large Array and modern projects like Breakthrough Listen, the signal never repeated. Theories abound. Was it a comet's hydrogen cloud reflecting Earth's own radio leakage? A glitch in the telescope's hardware? Or, as some still hope, a fleeting message from another civilization that switched off or changed frequencies before we could reply? The lack of answers has only fueled fascination, turning the WOW signal into a cultural touchstone, referenced in films, books, and even a symphony composed from its data. The signal's enduring legacy lies in what it represents, the tantalizing possibility that we might not be alone, and that the universe could be whispering secrets we're only beginning to tune into. Whether natural or artificial, the WOW signal reminds us how much we still don't understand about the cosmos, and how a single, unexplained blip on a printout can redefine our place in the universe. Our sun may seem calm most days, but even its occasional solar flares can unleash staggering energy equivalent to millions of hydrogen bombs detonating at once. Yet these eruptions pale in comparison to the cosmic monsters known as superflares, observed radiating from other stars. These aren't just scaled-up versions of Earth's solar storms. They're orders of magnitude more powerful, capable of sterilizing nearby planets and rewriting atmospheric chemistry in a single catastrophic burst. Take the Carrington event of 1859, the most intense solar storm ever recorded. When a massive coronal mass ejection struck Earth, telegraph systems worldwide sparked and caught fire, auroras lit up tropical skies, and compass needles spun uselessly. But here's the sobering truth. That historic storm was merely 1,000 times weaker than the superflares detected on ordinary sun-like stars. Modern telescopes like Kepler have spotted these beasts releasing energy equivalent to 100 million Carrington events in mere hours. One star, KSE 9856245, produced a flare so intense it briefly outshone the star itself, emitting ultraviolet radiation that would have vaporized the ozone layers of any orbiting planets. What makes these superflares so terrifying is their unpredictability. Unlike our Sun, which typically targets its worst outbursts at aging, magnetically active stars, these superflare stars often appear perfectly normal until they suddenly erupt like cosmic volcanoes. The secret lies in their tangled magnetic fields. When these fields twist too tightly, they snap like overwound rubber bands, releasing pent-up energy that accelerates particles to near light speeds. The resulting radiation barrage includes everything from X-rays to gamma rays, accompanied by plasma clouds massive enough to engulf entire solar systems. The implications are chilling. Had Earth been orbiting one of these stars during a superflare event, the intense UV and X-ray radiation could have stripped our atmosphere, boiled oceans, and extinguished all but the hardiest microbes. Even flares a tenth as powerful possible from younger, more active versions of our Sun might explain why Mars lost its water and atmosphere over time. Some scientists speculate that past superflares could account for mysterious extinction events in Earth's fossil record, where sudden radiation spikes left telltale isotopes in ancient rock layers. Yet there's a silver lining. By studying these stellar tantrums, we're learning how to better protect our technology-dependent civilization from milder solar storms. Early warning systems, hardened power grids, and radiation-shielded satellites all trace their development back to our growing understanding of these cosmic outbursts. Every superflare we detect serves as both a warning and a lesson, reminding us that in the grand cosmic arena, even seemingly stable stars can become agents of chaos without notice. Rising like colossal hourglasses from the Milky Way's core, the Fermi bubbles stretch 50,000 light-years into space, twin towers of gamma-ray energy towering over our galaxy's disk. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these faint but gargantuan structures glow with the afterburn of some ancient cataclysm, their origins whispered in high-energy particles rather than visible light. If human eyes could see gamma rays, the bubbles would dominate the night sky, each one spanning half the width of the full moon despite being 25,000 light-years away. The leading theory points to a violent feast by Sagittarius A, the supermassive black hole at our galaxy's heart. Between 1 and 3 million years ago, a blink in cosmic time, this gravitational monster may have gorged on an enormous cloud of gas or even a wayward star. As material spiraled into oblivion, the black hole's spin and magnetic fields could have funneled some of the infalling matter into dual jets, blasting them perpendicular to the galactic plane at near light speed. These jets would have plowed through the Milky Way's diffuse halo gas, creating shock waves that accelerated particles to extreme energies, leaving behind the bubbles we see today as fading evidence of the eruption. But there's a twist. The bubbles aren't perfectly symmetrical. The northern structure extends slightly farther than its southern counterpart, and both show intricate substructures, filaments, and edges suggesting multiple outbursts rather than a single event. This has astronomers debating whether Sagittarius erupted in repeated hiccups or if the bubbles were sculpted by something even wilder, like a swarm of exploding stars or dark matter annihilations near the galactic center. What makes these bubbles truly astonishing is their longevity. Unlike fleeting supernova or gamma-ray bursts, the Fermi bubbles have persisted for millions of years, their slow decay offering a rare window into the Milky Way's explosive past. Their gamma-ray glow comes from cosmic rays' high-energy protons, colliding with gas particles, a process that creates secondary particles called pions, which then decay into gamma rays. This lingering radiation lets us study the aftermath of an eruption we missed by cosmic seconds. The implications stretch beyond our galaxy. If such outbursts are common, they could explain similar structures seen in other galaxies where black hole burps regulate star formation by heating surrounding gas. The Fermi bubbles remind us that even quiet galaxies like ours have violent histories, and that the darkest objects in the universe can sculpt the cosmos on scales almost too vast to comprehend. Every gamma-ray photon we detect from these structures carries echoes of a cataclysm so grand it shaped the Milky Way itself. Deep in the invisible scaffolding of the cosmos, where dark matter outpaces ordinary stuff 5-to-1, physicists wonder, could this mysterious substance be hiding its own brand of cosmic fireworks? The idea isn't as far-fetched as it sounds. If dark matter particles occasionally collide and annihilate, transforming into bursts of gamma rays, electrons, and other known particles, these invisible interactions might light up the universe in ways we're only beginning to detect. Take the galactic center gamma ray excess, a puzzling glow of high-energy radiation emanating from the Milky Way's core. While some attribute it to pulsars or other astrophysical sources, others see fingerprints of dark matter annihilation. Theoretically, if dark matter particles are their own antimatter counterparts, a property known as being Majorana, they could obliterate each other on contact, releasing energy in the process. The gamma rays we observe could be the aftermath of countless such annihilations happening right under our noses, hidden in plain sight, but the plot thickens. Not all dark matter models predict explosive signatures. Some theories suggest these particles interact so weakly that annihilation would be vanishingly rare, while others propose they might decay slowly over eons, emitting subtle radiation rather than dramatic bursts. Then there's the tantalizing case of dwarf spheroidal galaxies, small, dark matter-rich satellites of the Milky Way. These dim celestial objects show faint gamma-ray halos that stubbornly resist explanation by known astrophysics, leaving room for dark matter as a potential culprit. The search for these phantom explosions is pushing technology to its limits. Instruments like the Fermi Gamma Ray Space Telescope and upcoming observatories such as the Cherenkov Telescope Array scan the skies for anomalous gamma-ray patterns that could betray dark matter's secrets. Meanwhile, underground labs hunt for indirect evidence in the form of exotic particles or unexpected cosmic ray fluxes. What's at stake goes far beyond academic curiosity. If dark matter annihilation proves real, it could rewrite our understanding of particle physics, revealing a hidden sector of the universe where matter and energy behave in ways the standard model never predicted. Even null results are valuable, narrowing the possibilities and forcing theorists back to the drawing board. Every unexplained gamma-ray photon or peculiar particle detection brings us closer to answering one of cosmology's biggest questions. Is the universe's missing mass silently exploding all around us, leaving traces only the most patient observers can decode? Long before the first stars ignited, before galaxies took shape, even before matter as we know it existed, the universe began with the most titanic explosion of all, the Big Bang. But unlike the fleeting brilliance of supernova or gamma-ray bursts, this primordial detonation left behind something far more subtle yet enduring, a whisper from the dawn of time itself, imprinted across the entire cosmos. We call it the cosmic microwave background, and it's the oldest light we can see, a snapshot of the universe when it was just 380,000 years old, stretched and cooled over billions of years until it reached us as a faint glow of microwave radiation. Imagine the universe in its infancy, a seething, opaque plasma so hot that light couldn't travel far before being absorbed and re-emitted. As expansion gradually cooled this fiery soup, protons and electrons finally combined to form neutral hydrogen atoms, allowing photons to stream freely for the first time. This moment of recombination released a flash of light that has been traveling ever since, its wavelength stretched by the expanding universe from visible light into microwaves. Today, that light fills every cubic centimeter of space, a relic radiation carrying fingerprints of the universe's earliest structures. What's astonishing isn't just its existence, but what it reveals. Tiny fluctuations in the cosmic microwave background, regions slightly hotter or cooler than average, correspond to density variations in the early universe. These minuscule ripples, some as small as 1 part in 100,000, were the seeds of all cosmic structure. Over eons, gravity amplified them, pulling matter into the web of galaxies and clusters we see today. Without these imperfections, the universe would be a featureless void, no stars, no planets, no us. The discovery of this cosmic echo was almost accidental. In 1965, radio astronomers Arno Penzias and Robert Wilson stumbled upon an inexplicable hiss in their antenna, a uniform noise that persisted no matter where they pointed it. After eliminating every possible source of interference, including pigeon droppings in their telescope, they realized they'd found the afterglow of creation itself. Their Nobel Prize-winning detection confirmed a key prediction of the Big Bang theory, silencing rival models and cementing our modern understanding of cosmic origins. Yet the cosmic microwave background isn't just a static relic. Modern satellites like Planck and WMAP have mapped its subtle variations with breathtaking precision, revealing details about the universe's composition, age, and even its ultimate fate. The patterns tell us that ordinary matter, the stuff of stars and planets, makes up less than 5% of the cosmos, while dark matter and dark energy dominate the rest. They even hint at a brief period of exponential expansion called inflation, which smoothed the early universe and set the stage for everything that followed. So when you tune an old television to static, a fraction of that snow is literally the universe's birth cry, light from the edge of time, diluted but never entirely faded. It's a reminder that the grandest explosions aren't always the loudest, and that sometimes the most profound secrets are hidden in the faintest signals, waiting for us to listen. The universe as we know it might be sitting on a knife's edge, not just physically but mathematically. Hidden in the equations of quantum field theory lies a chilling possibility that everything we consider reality exists in a false vacuum, a seemingly stable state that could at any moment collapse into something entirely different. This isn't science fiction, it's a legitimate, albeit speculative, scenario called vacuum decay, where the very laws of physics could be rewritten in an expanding bubble of annihilation. Picture the universe like a marble resting in a valley. Right now, it's settled comfortably at the lowest point, what physicists call the true vacuum, the most stable state of energy. But what if that valley is just a small dip on a much larger hillside? Our entire cosmos might actually be perched on a precarious ledge, with a far deeper valley, a lower energy state lurking somewhere beyond. If quantum fluctuations or high-energy experiments somehow nudge the universe over that ledge, the effects would be catastrophic. A bubble of true vacuum would form, expanding outward at the speed of light, rewriting the fundamental constants of nature in its wake. Atoms would disintegrate, forces like electromagnetism and gravity would cease to function as we know them, and reality itself would unravel, the scariest part. We wouldn't see it coming. The bubble's boundary would move so fast that by the time light from its edge reached us, destruction would already be imminent. One moment, everything's normal, the next, the universe as we know it vanishes without warning. Some theories suggest this could have already happened elsewhere in the cosmos, with doom expanding toward us undetected. Yet there's a twist. Vacuum decay isn't just doom and gloom. It hints at something profound about our universe, that the laws we take for granted might be arbitrary, a local accident in a much vaster multiverse where different physics reign. If true, it means our reality is fragile, a temporary island of order in a sea of infinite possibilities. For now, vacuum decay remains hypothetical, with no evidence it's happening or even possible. But the fact that our best physics entertains such an idea is both humbling and exhilarating, a reminder that the universe still holds mysteries far stranger than anything fiction could invent. In 2015, astronomers caught a flare of light so brilliant it defied classification, a cosmic beacon dubbed Assassin 15 LH, shining with the luminosity of 570 trillion suns. At first glance, it looked like the most powerful supernova ever recorded, outshining typical stellar explosions by 200 times. But as researchers pored over the data, they realized this event was anything but ordinary. The more they studied it, the more they questioned whether they were witnessing a supernova at all, or something far stranger. The first clue lay in the numbers. A normal core collapse supernova might peak around 10 billion times the sun's brightness, but Assassin 15 LH reached nearly 600 times that intensity. Its energy output didn't just break records, it shattered the existing models for how stars die. Even more puzzling was its location, flaring from the outskirts of a large, passive galaxy where massive stars, the kind that produce supernova, are rarely born. This was like finding a wildfire in the middle of an ice field, defying expectations at every turn. As the debate heated up, an alternative explanation emerged. What if this wasn't a supernova, but a star being torn apart by a hidden black hole? Tidal disruption events, where a black hole's gravity shreds a passing star, can produce flares of comparable brightness. But here, too, Assassin 15 LH refused to fit neatly into the box. The galaxy hosting the explosion lacked the typical signs of a supermassive black hole at its core, and the flare's light curve didn't match the steady fade expected from a star's debris settling into an accretion disk. The plot thickened when astronomers detected signs of hydrogen in the explosion's aftermath, a fingerprint rarely seen in tidal disruptions but common in certain types of supernova. This led to a third, even more exotic possibility: a magnetar-powered supernova. Imagine a newborn neutron star spinning so fast with a magnetic field so strong that it acts like a cosmic dynamo, pumping energy into the exploding star's ejector and supercharging its brightness. The math suggested such an engine could explain Assassin 15 LH's extreme luminosity if the magnetar's spin and magnetic field were pushed to theoretical limits. Yet years later, the mystery persists. Some researchers argue for a hybrid scenario. Perhaps a star already swollen to enormous size was disrupted not by a supermassive black hole, but by an intermediate mass black hole lurking where none was expected. Others propose entirely new categories of explosions, where stars in rare environments meet bizarre ends we've yet to fully comprehend. What makes Assassin 15 LH so compelling isn't just its record-breaking brilliance, but how it exposes the gaps in our understanding. Even in an era of advanced telescopes and supercomputers, the universe can still conjure explosions that leave us questioning everything we thought we knew. Whether it's a supernova on steroids, a black hole's messy meal, or something entirely new, this cosmic enigma reminds us that the most extreme events often resist easy labels. And that's where the real discovery lies, not in fitting nature into our boxes, but in letting its surprises redraw the boundaries of what's possible. Just moments after the Big Bang, the universe didn't just expand, it exploded outward faster than the speed of light, stretching from a subatomic speck to something astronomically vast in a fraction of a second. This wasn't your average expansion, it was cosmic inflation, a runaway growth spurt so extreme it makes even the most energetic supernova look like a candle flicker. And while we often think of explosions as destructive, this one was creative, sculpting the very fabric of the cosmos into the universe we recognize today. Imagine blowing up a balloon, but in the time it takes to blink, that balloon grows from the size of a grape to larger than the observable universe. That's inflation, an exponential surge driven by a mysterious form of energy woven into space itself. As this energy dominated the early cosmos, it didn't just stretch space, It amplified quantum fluctuations, tiny ripples in the newborn universe, into the seeds of galaxies. Those microscopic wrinkles became the blueprints for galaxy clusters, the cosmic web, and everything in between. Without inflation, the universe might have remained smooth and featureless, no stars, no planets, just a vast, dull emptiness. But here's the kicker: inflation didn't just shape space, it left behind echoes we can still detect. The cosmic microwave background, that ancient afterglow of the Big Bang, carries faint temperature variations, imprints of those stretched quantum fluctuations. Some spots are slightly hotter, others cooler, matching the density variations that gravity later sculpted into galaxies. It's like finding the fossilized footprints of the universe's first explosive growth spurt. What powered this frenzy? Theorists point to a hypothetical field called the inflaton, a sort of cosmic fuel that temporarily turbocharged expansion before decaying into the particles and radiation we know today. The transition was anything but smooth. As inflation ended, its energy reheated the universe, igniting the hot plasma of the Big Bang's afterparty. Think of it as the universe hitting the reset button, swapping exponential expansion for the steadier growth we see now. Yet mysteries linger. Why did inflation start or stop? Are there other universes where it never ended, forever stretching beyond our horizon? Some models suggest our cosmos is just one bubble in an infinite multiverse, each with its own physics, born from eternal inflation. It's a dizzying thought, but one that underscores inflation's dual role, both the universe's most violent energy release and the quiet architect of everything we know. The next time you gaze at the night sky, remember those distant galaxies owe their existence to a primordial explosion so vast it set the stage for reality itself. Deep in the heart of our galaxy, about 3,500 light-years from Earth, lurks a cosmic predator with an appetite so voracious it's earned the nickname the Great Annihilator. Officially catalogued as 1E1740.7-2942, this black hole isn't just consuming matter. It's unleashing jets of antimatter into space, creating some of the most energetic phenomena astronomers have ever witnessed. What makes this system so extraordinary is the violent dance between matter and antimatter happening near its event horizon. As gas and dust spiral toward the black hole, they form a superheated accretion disk reaching temperatures of millions of degrees. But here's where physics gets weird. Instead of simply plunging into oblivion, some of this material gets funneled into powerful jets shooting outward at nearly light speed. These aren't ordinary jets, they're packed with positrons, the antimatter counterparts to electrons. When these positrons eventually collide with normal electrons in interstellar space, they annihilate each other in flashes of gamma-ray light at precisely 511,000 electron volts, the telltale signature of matter-antimatter destruction. The first hints of this cosmic drama emerged in the early 1990s, when gamma-ray telescopes detected an intense source near the galactic center emitting radiation at that exact energy. No natural process besides positron annihilation could produce such a precise signal, immediately marking 1E1740.7-2942 as something special. Follow-up observations revealed even more bizarre behavior. The jets sometimes flip direction abruptly, as if the black hole's magnetic field lines are snapping and reconnecting like cosmic rubber bands. But the real puzzle lies in where all these positrons come from. Theoretical models suggest they're created in the extreme environment just outside the event horizon, where temperatures and magnetic fields are so intense that particle-antiparticle pairs spontaneously emerge from the quantum vacuum. Most annihilate instantly, but the black hole's powerful jets can funnel some positrons away before they meet their fate, allowing them to travel light years before eventually colliding with electrons and lighting up the galaxy with their final explosive embrace. This ongoing annihilation has broader implications for our understanding of the Milky Way. astronomers estimate that the Great Annihilator and similar objects could be responsible for the mysterious fog of 511,000 electron-volt gamma rays permeating our galaxy's center, a glow that had baffled scientists for decades before this discovery. Every annihilation event we detect is a reminder that even the darkest objects in the universe can become cosmic alchemists, transforming matter into energy with an efficiency no human-made reactor could ever hope to match. So while black holes might be famous for what they destroy, this one proves they can also create, or at least unravel, the very fabric of reality in ways we're only beginning to comprehend. On October 9, 2022, satellites scanning the skies for gamma-ray bursts suddenly lit up like a Christmas tree, a signal so intense it overloaded detectors across multiple spacecraft. Designated GRB 221009A, this explosion quickly earned the nickname "Boat Brightest of All Time," and for good reason. Blasting from a galaxy nearly 2 billion light-years away, it unleashed more energy in its first few seconds than our Sun will produce in its entire 10-billion-year lifespan, making it the most luminous gamma-ray burst ever recorded in human history. What set BOAT apart wasn't just its raw power, it was how that energy reached Earth. Unlike typical gamma-ray bursts where the beam's narrow focus might miss us entirely, this one arrived almost perfectly aligned with our planet. The result, a hailstorm of high-energy photons so intense they created a phenomenon called ringing, where charged particles in Earth's upper atmosphere reverberated like a struck bell. Even more astonishing, the afterglow remained detectable for months, shining brighter than a million supernovae as it revealed never-before-seen details about the physics of these cosmic detonations. Scientists quickly realized BOAT was a once-in-a-millennium event. Its light carried fingerprints of heavy elements forged in the explosion, including tellurium, a rare metal that helped confirm these bursts are cosmic factories for elements heavier than iron. But the real surprise came when telescopes detected the highest energy photons ever observed from a gamma-ray burst. Tera-electron-volt gamma rays packing 1 trillion times more energy than visible light. These extreme particles challenged existing theories about how relativistic shocks accelerate matter, forcing physicists to rethink decades-old models. The burst's aftermath also provided a front-row seat to stellar death on an epic scale. Analysis suggested BOAT originated from a massive star collapsing into a black hole. But with a twist, the progenitor star may have been spinning unusually fast, amplifying the jet's power through a cosmic dynamo effect. This spin could explain why the burst outshone its predecessors by a factor of 10, offering clues about the exotic conditions that breed such extreme explosions. Yet BOAT's legacy extends beyond astrophysics. Its light traveled through dust clouds in its host galaxy, allowing astronomers to map interstellar material in unprecedented detail, like using a cosmic flashlight to illuminate the hidden structure of another galaxy. The event even sparked discussions about radiation hazards, as researchers calculated that a similar burst within a few thousand light-years could have catastrophic consequences for life on Earth. In the end, GRB 221009 wasn't just a record breaker, it was a Rosetta Stone for high-energy astrophysics, rewriting textbooks while leaving behind a treasure trove of data that will fuel discoveries for decades. Every time we think we've seen the universe's limits, cosmic events like BOAT remind us, the most violent explosions aren't just destructive, they're the universe's way of showing us where the next frontier lies. Picture the universe as a rubber sheet stretching in every direction, not just expanding but accelerating outward so rapidly that distant galaxies appear to flee from us at ever-increasing speeds. This isn't just expansion, it's a cosmic explosion in slow motion, driven by a force so mysterious we've named it dark energy. Unlike the fiery detonations of supernova or gamma-ray bursts, this phenomenon doesn't tear through space, it rewrites the very fabric of spacetime itself, pushing galaxies apart with a relentless, invisible pressure. The discovery of this acceleration in the late 1990s sent shockwaves through astronomy. Two teams studying distant supernova made the same baffling observation. These cosmic yardsticks, expected to reveal the universe's deceleration due to gravity, were actually dimmer than predicted. The only explanation, space itself was stretching faster over time, as if some unseen hand had flipped a switch on the cosmos's expansion. Dark energy, constituting roughly 68% of the universe's total energy, became the leading suspect, a repulsive force embedded in the vacuum of space, growing stronger as the universe grows larger. What makes dark energy so unsettling is how little we understand it. The simplest model treats it as a cosmological constant, a fixed energy density filling space uniformly like a never-ending fog. But there's a problem. Quantum field theory predicts a vacuum energy trillions of times stronger than what we observe. If dark energy matched those predictions, galaxies would have been ripped apart before they could even form. This staggering discrepancy, known as the cosmological constant problem, remains one of physics' greatest unsolved puzzles, yet the evidence for dark energy's effects is everywhere. Look at the large-scale structure of the universe. Galaxy clusters drifting apart like flotsam on an inflating balloon, their light stretched into longer, redder wavelengths by the expansion. Even the cosmic microwave background carries its fingerprints, subtle patterns in the ancient glow, revealing how dark energy's push has shaped the universe over billions of years. The most chilling implication: if this acceleration continues unchecked, the universe could end in a big rip, where dark energy overwhelms gravity entirely, shredding galaxies, stars, and eventually atoms themselves. Or perhaps dark energy will fade, allowing gravity to pull everything back into a fiery collapse. Right now, we're left watching the ultimate cosmic explosion unfold in ultra-slow motion, a silent, invisible detonation that may one day dictate the fate of everything. Every star that explodes, every black hole that merges, every galaxy that collides, they're all threads in the universe's grand tapestry, weaving toward an inevitable conclusion. But what happens when the cosmic fireworks finally burn out? The universe's most violent explosions don't just shape its present, they're signposts pointing toward its ultimate fate, whether that's a cold, silent fade into darkness or a dramatic rebirth in fire. Consider heat death, the most widely accepted scenario. As the cosmos expands, galaxies drift apart like embers from a dying fire, their stars slowly burning out one by one. Supernova and gamma-ray bursts, once common, become rare events as star-forming gas is exhausted. Black holes, having feasted on the remains of galaxies, themselves evaporate over incomprehensible timescales through Hawking radiation. The universe reaches maximum entropy, no energy gradients, no motion, just a uniform sea of particles diluted across infinite space. It's not an explosion but an implosion of possibility, the ultimate stillness where even time loses meaning. But there's a more violent alternative, the Big Rip. If dark energy's repulsive force grows stronger over time, it could eventually overpower gravity, electromagnetism, even nuclear forces. First, galaxies would tear apart, then stars, then planets finally. Atoms themselves would be shredded in the last femtosecond of existence. The cosmos wouldn't just fade, it would explode from within, every structure rupturing as space itself becomes the ultimate demolition force. In this scenario, today's supernova are mere firecrackers compared to the universe's final, catastrophic rupture. Yet some theories offer a dramatic third act, cosmic rebirth. If the universe is cyclic, each Big Bang might be preceded by a big crunch, where gravitational collapse triggers a new inflationary epoch. In this view, every hypernova and gamma-ray burst is recycling matter for the next cosmic cycle, like phoenix ashes awaiting reignition. Certain string theory models even suggest colliding brains in higher dimensions could reset reality. turning our universe's death throes into the labor pains of a new one. The most haunting realization: these outcomes aren't abstract, they're written in the light of every explosion we observe. When astronomers measure how supernova accelerate the universe's expansion, or when they study how black hole mergers warp space-time, they're gathering clues about the cosmos' final chapter. The same forces that power today's most energetic events, gravity, dark energy, quantum fluctuations, will one day decide whether the universe ends with a whisper, a scream, or an encore. So when we witness a gamma-ray burst or a colliding neutron star, we're not just seeing the universe's past, we're glimpsing its future. Every cataclysm is a rehearsal for the final act, where Chinese letter isn't a single galaxy or star system, but reality itself. The explosions we marvel at today may one day be the last sparks in an expanding void, or the first notes of a symphony we can't yet imagine. After 30 facts about the universe's most violent explosions, one question lingers: could these cataclysmic events hold the key to life itself? It's a cosmic paradox. The same forces that rip stars apart and flood galaxies with lethal radiation might also be the architects of life's building blocks. Take Earth, for example. The iron in our blood, the calcium in our bones, even the gold in our jewelry, all were forged in the furnaces of dying stars and scattered across space by supernova and kilonovae. Without these explosions, our planet would be little more than a barren rock, devoid of the heavy elements essential for complex chemistry, let alone biology. Yet there's a flip side. A gamma-ray burst too close to home could strip away our ozone layer in seconds, bathing the surface in deadly ultraviolet radiation. Some scientists even speculate that one such burst might have triggered a mass extinction 450 million years ago, wiping out nearly 80% of Earth's species. It's a delicate balance. Too many nearby explosions and life gets scorched away. Too few, and the universe remains a hydrogen wasteland, starved of the ingredients needed for planets or people. This Goldilocks zone extends beyond chemistry. The energy released by these explosions shapes galaxies, carving out regions where stars form at just the right pace. Not so slowly that heavy elements stay locked in dying stars, but not so rapidly that radiation sterilizes entire systems. Even black holes play a role. The fury of quasars and active galactic nuclei can heat surrounding gas, preventing it from collapsing into new stars too quickly. In quieter galaxies like ours, this regulation allows for stable solar systems where life might have time to emerge and evolve. Perhaps the most humbling thought is this: every civilization that ever existed or ever will owes its existence to a chain of cosmic violence stretching back to the Big Bang. The universe had to explode, collapse, and explode again countless times just to create the conditions where a species could look up at the night sky and wonder if it's alone. So the next time you hear about a distant supernova or a colliding neutron star, remember, you're not just witnessing destruction. You're seeing the universe's messy, violent, and breathtakingly creative process of trial and error, where death and rebirth are woven into the same cosmic tapestry. And somewhere in that balance between the chaos and the calm, life finds a way. The irony is as profound as it is poetic. To ask if we're alone is to ask if the universe has struck that perfect equilibrium, where its most destructive forces somehow, against all odds, became the very reason we're here to ask the question at all. From gamma-ray bursts that outshine galaxies to hypernova that rewrite the rules of physics, we've journeyed through 30 astonishing facts about the universe's most violent explosions, events so powerful they shape the cosmos itself. These aren't just cosmic spectacles, they're the engines of creation, forging elements, sculpting galaxies, and even influencing the conditions that made life possible. Think about it: the gold in your jewelry, the iron in your blood, and the uranium powering cities were all born in the heart of dying stars, scattered across space by these cataclysmic blasts. Without them, the universe would be a barren, chemical wasteland, no planets, no oceans, no us. But the story doesn't end there. These explosions are more than just relics of destruction. They're active participants in the universe's evolution. When neutron stars collide, they seed the cosmos with precious metals. When quasars flare, they regulate star formation across entire galaxies. Even the faint afterglow of a gamma ray burst acts as a cosmic time machine, letting us peer back to the universe's infancy. Every detonation, every collision, every eruption is a thread in the tapestry of reality, weaving together the past, present, and future of everything we know. Now we want to hear from you. Which fact left you awestruck? Was it the kilonova that forged the gold in your phone, or the magnetar flare that outshone the moon? Maybe you're still grappling with the idea of vacuum decay, the universe's silent, theoretical time bomb. Drop your thoughts in the comments below and let's keep the conversation going. After all, the universe's greatest mysteries aren't just for scientists to solve. They're for all of us to wonder about, debate, and explore together. If you've enjoyed this deep dive into the cosmos's most explosive phenomena, don't miss out on what's next. Hit that subscribe button to join us as we unravel more mind-bending space mysteries, from the enigmas of dark matter to the secrets of rogue black holes. The universe is vast, violent, and endlessly fascinating, and we're just getting started. Until next time, keep looking up. The cosmos has plenty more surprises in store.